Okay, so welcome to the lecture of this finite volume method, and we will continue our discussion on diffusion equation. What we have done so far is that essentially looking at the two dimensional system, and just to before begin with, we just quickly give you a recap. This is the governing equation that we have looked into, and the elemental control volume that we have considered is C, and the ahead of it east, downstream of it west, then top north and bottom south. This was the two dimensional stencil or the discretized indexing that we have taken for some interior node. This is for any interior element. So, considering an interior element, we have actually derived the discretized system from this system. So, what are the convention? So, once we finally use that, this is the face E, this is the face west, this is the face south and north. These are the surface vector that are used in the derivation of that. So, this is AC, this is SN, this is SW, this is SS. So, all this SI essentially or SF, these are the surface normal vector, where F goes from east, west, north, south, and also this two dimensional grid system is uniform. So, it was a uniform system. So, we had this one delta x, similarly this one also delta y. So, once we have done the discretization, this governing equation actually gets us this AC phi c plus AE phi E plus AW phi W plus AN phi N plus AS phi S equals to BC. So, this is the discretized equation that we obtained for any interior element. Any interior element is governed by this particular set of. So, essentially this discretized equation is going to get you the Ax equals to B, and while doing this, all our coefficients were essentially in a compact form. If one has to write in a compact form, then it was AC phi c plus summation of F, it goes over the faces AF phi F equals to BC, and all these coefficients like AF was flux FF, which is minus gamma F dF, AC was summation of small f goes from all the faces equals to flux, and BC is QC BC minus summation of all the small faces flux BF, and capital F in all these stands for east, west, north, south. This is for elements. So, the element C is sort of surrounded by all these 4 elements east, west, north, south, and small f is essentially the corresponds to the faces. So, the face like this is C, E face is a common face between element E and C, north face is a common face between N and C, west face is a common face between C and the west element, and the S face is between. So, this is what we obtain, and then to get the solution done we need to apply for the boundary condition. The first type of boundary condition that we have applied is the Dirichlet boundary condition. So, Dirichlet boundary condition. So, this one, and then accordingly we have modified the system, and the modified equation was obtained. Now, the second kind of boundary condition. So, this was also discussed in the earlier lecture. So, the next one, so what happened when we apply the boundary condition? Essentially this is the governing equation. Now, this actually valid for all the interior elements, but when it comes down to the boundary element or the face at the boundary, this particular equation needs to be modified. For example, when we had a boundary at east face, the contribution for this cell will get drops down. At the same time, some terms will appear at the source term due to the specified variable. Similarly, if the boundary face belongs to north, automatically this guy would goes off, the north contribution. If it is at the west, the AW phi W goes off. If it is the south, AS phi S goes off. So, that is how for a Dirichlet boundary condition one can arrive the cell. Now, we will look at the second type of boundary condition is the Neumann boundary condition. So, for that, if you just look at that element, then you see how that Neumann boundary condition can be applied. So, this is my face, and this would be the boundary face. This is element C, this is south, this is west, this is north, this is northwest, this is southwest, and this face is the, and here now this is the point B and the Neumann condition. So, this is the direction of the surface vector, this will be the direction of the south face surface vector SW SN. Now, the Neumann condition is nothing but something, the gradient is minus del phi b dot NB equals to Q specified. So, that is the Neumann boundary condition. So, essentially what does that mean? The gradient at that particular face. So, now if you look at that element C, which actually one of its face, the east face belongs to the boundary, the gradient condition is prescribed. So, the condition which is prescribed at the boundary face, that B, is minus gamma del phi b dot I equals to QB. In other words, one can write the diffusion flux at dot B equals to minus gamma del phi b dot SB I, which will be QB SB, which is equivalent to the flux which is defined there, CB phi C plus flux VB, and these are the coefficients. So, these coefficients one need to find out, and if you look at this particular condition, they turn out to be the flux Cb would be 0 and the flux Vb would be Qb Sb, which is essentially Qb delta y C. So, that is what you get. Now, one thing you can note here, the sign of the flux component, the sign of flux is assumed to be positive. That is why it has been considered pointing outward. Now, this equation of the QB or the information of the QB, this could be directly included in the system, and like this could be directly imposed in this particular equation, and what we can get. So, once you apply all of the above conditions, what we get AC phi C plus AW phi W plus AN phi N plus AS phi S equals to BC. So, again if you look at this particular equation, it looks exactly similar to the condition that we derived for the Dirichlet boundary condition. So, but that does not mean they would be of similar expression. The mathematical expression or the discretized system looks similar, the reason being both the boundary condition, whether the phi be specified, the Dirichlet boundary conditions or the Neumann boundary condition currently which we are talking or discussing, both of them have been applied at this particular phase, which is at the east phase. So, the commonality between them is that both of them are applied or considered at east phase. That is why the representative discretized equation, they look similar, but the points which are going to be different is that A is 0 here, AW would be flux FW which is minus gamma W dW, AN is flux Fn which is minus gamma n dn, AS is flux Fs which is gamma s ds, and we have AC which is summation of phases and flux Cf. Essentially that becomes AW plus AN plus AS. Okay. And the difference would appear in this particular source term, the BC, which is going to be now QC BC minus flux BB plus summation of over the faces flux BF. This is the difference that would appear for the Dirichlet Neumann boundary condition. Now, there are few important comments, so or observation for these things. One of the important observation is that this Neumann boundary condition does not result in a dominant AC coefficient. That is a very important observation. Number 2, if both QB and SC are 0, then phi c is bounded by its neighbors. Otherwise, what can happen? Phi c can exceed or fall below the neighbor value of phi, whichever is admissible. Now, for example, and you can get it more clear, for example, if phi, let us say, represent temperature, phi is equivalent to temperature. If phi is temperature and QB represents the heat flux, so heat flux applied at the boundary, that means either the heat is added or heat is taken out from the boundary, then the region close to that boundary, it is expected to have higher or lower temperature compared to that interior. So, that is what it says, that whatever information you have, accordingly they would be bounded. Now, third point, once phi c is computed, once that is computed, the boundary value phi b can be computed as phi b equals to gamma b dB phi c minus QB divided by gamma b dB. So, from the phi c, once that elemental variable is calculated, you can calculate back the specified value. And the last one is that actually this Neumann condition, can be treated as natural boundary condition for finite volume method, for boundary condition for FVM, because this means whenever we are dealing with some flows or heat transfer related problem, if the flux is specified, that is quite handy to implement in finite volume method. So, whether in terms of discretization of that particular phase element or other way around. So, these are certain observation that is there. Now, the third kind of boundary condition is the mixed boundary condition. So, mixed boundary condition, which will mean if we again draw these elements and apply the boundary condition. So, this is my element C, this should be north, this is west, this is south, and the boundary condition which is applied here, this is point B. So, here the boundary condition which is applied at phi infinity, h infinity and phi b. So, both of them are specified. So, these are the surface normal vector, northwest, southwest. and this is the face of the boundary. So, this is the boundary face. Now, again the condition here is specified to the mixed condition. So, you have a some sort of a heat transfer coefficient or convective heat transfer coefficient is specified, which is based on H infinity. Now, the flux which one can write for that is minus gamma del phi B dot I S B, which is going to be minus H infinity into phi infinity minus phi B into delta y c. Okay. So, here you got the both the information in the mixed boundary condition, which is another way people call it a Rabin boundary condition or mixed boundary condition, where you have both the Neumann kind of boundary condition given a flux and also the specified value is also provided. So, both of them are acted simultaneously at the same phase. So, if you rewrite this expression, one can write gamma B S B phi B minus phi C by delta x B, which is minus H infinity phi infinity minus phi B S B. So, that is what it gets you back. Now, once you get back this, you can find out phi B from the above expression, which is going to be as H infinity phi infinity plus gamma B divided by del x B into phi C H infinity plus gamma B divided by del x B. Now, this one you apply it back in this particular flux information. So, the information of phi B, once you input this to the flux expression, one can get J B dot is B equals to minus H infinity gamma B by del x B divided by H infinity plus gamma B by del x B S B into phi infinity minus phi C, and this particular term one can think about as an resistance or some sort of an equivalent resistance, and you represent this one as R eq. So, it is an some kind of an resistance which is applied here, which is also it can be written as two coefficient, one is flux C B phi C plus flux V B. So, you got the expression for the flux which is applied there, and using the information of the given value you find out these coefficients, where flux C B is nothing but this R equivalence and flux V B is minus R equivalent into phi infinity. So, once you use this information and again put it in the, so the obtained discretized equation would have the expression like AC phi c plus A w phi w plus A n phi n A s phi s equals to B c. Again, if you look at the similarity between your Neumann condition, the expression which is obtained here and the expression which is obtained for the mixed condition, they look similar algebraically, or notation wise they look exactly similar, and the reason is, as I have said earlier, this is going to be applied at the east face of this cell. This is my C element and all these boundary conditions are applied at the east face. If it would have been applied to the other faces like west, north or south, those corresponding contribution terms would go away, but the differences lie in the calculation of these coefficients and also B c. So, in the similar fashion for this mixed case, we get A equals to 0, A w would be flux F w which is minus gamma w d w, A n is flux F n which is minus gamma n d n, A s is flux F s which is minus gamma s d s, and A c is flux C b plus summation over faces of flux C f, which is going to be flux C b plus flux C w plus flux C n plus flux C s, and my B c is the Q c V c minus flux B v plus summation over faces for flux B f. Okay. So, though the discretized algebraic equation looks similar for all sort of conditions like Dirichlet condition, Neumann condition and mixed condition, but the differences lie in the expression of these coefficients and the source term. Now, having said that, we will move to the, these are the primary three boundary conditions which one can come across while applying the boundary condition for a physical problem. Either you have a specified value or you will have an applied flux. Let us say for example, if you are dealing with a flow through a channel, this is the inlet, this is the outlet. At the outlet, one can always assume the flux is 0. So, that is a sort of a Neumann boundary condition, or in some cases where you may have both the Dirichlet and Neumann applied together, which correspond to the mixed condition. Now, moving ahead, there would be fourth type of boundary condition which can be also used, which is a symmetric boundary condition. Now, typically along a symmetric boundary, the normal flux to the boundary of a scalar variable phi is 0. So, symmetry boundary condition is sort of equivalent to Neumann kind of boundary condition. Neumann boundary condition. So, there is a equivalency between symmetry boundary condition with the Neumann boundary condition, because what it says that is the normal to that boundary, the flux of the variable is 0. So, if it is equivalent to the Neumann boundary condition, so that means it will give rise to that flux Cb or flux Vb, they are 0. So, the discretized equation which can be modified for symmetry boundary condition and again can be written as, if the symmetry boundary condition again applied at the east face. This is my C, it is applied at east face. So, the discretized equation would look like AC phi C plus AW phi W plus AN phi N plus AS phi S equals to BC, where again you get AE 0, AW is nothing but my gamma W dW, A naught is gamma N dN, AS minus gamma S ds, and AC is nothing but minus AW AN plus AS, and BC would be my QC BC minus summation of faces flux BF. So, we have actually looked at a particular stencil when it exposed to the boundary condition, or rather different kind of boundary condition, starting from Dirichlet boundary condition, Neumann type boundary condition, mixed boundary condition and symmetry boundary condition. The discretized equation can be obtained and the corresponding coefficients can also be obtained accordingly. Now, if in all these cases that we have discussed, we have applied the condition at the east face. So, if we apply the condition on the other faces, then as I have been saying that the respective coefficients will go away and corresponding contribution or equivalent contribution should appear in the source term. So, that actually talks about the application of this boundary condition. So, we will stop here and thank you.